The last section of writing the ionic formulas of ionic compounds involves polyatomic ions. We haven't really talked much about polyatomic ions, so we will talk about what they are right here. A polyatomic ion. A polyatomic has three parts to its name. The first is the word poly, which means more than one. Atomic means atom. So polyatomic means it's going to have more than one atom with it. And then the word ion means that that package of two or more atoms is going to have a charge to it. So for example, this is called hydroxide. You have an oxygen atom and a hydrogen atom bonded together with an overall charge on the whole thing as -1. Okay? For these polyatomic ions, the first thing is that you will see this written as OH -1 in a table. These two atoms are set and fixed. You can't mess around or touch the subscripts on them. There is a set ratio between the O and the H. So they come as a package. You can't separate, you can't manipulate, you can't change anything about the O or the H and the subscript. Okay? They are set in stone. They behave as if they were one atom ion. Okay? So when we drop and swap, for example, the reason I mention this now is if you drop and swap and say there is a subscript, let me just do like, for example, Al plus 3, and let's say we have OH, it's not. Let me go over here. Al plus 3, and say you have hydroxide -1. When you drop and swap, that 3 from the aluminum has to go around the entire hydroxide. So what you end up with is Al parentheses OH3. That 3 has to apply to both the O and the H. So use a parentheses to show that that OH is not separate, but rather a package. What you don't want to do is this, because this happens all the time. People will write AlOH3, and the 3 will just appear to be attached to the O, or I'm sorry, just attached to the H. You can't do it that way. OH is a package, so that 3 applies to both the O and the H. Okay, so this little flow chart kind of helps you get through some of these ionic compounds because there's sort of a lot to think about. So you know you have an ionic compound if you have a metal. So is there a metal? If the answer is yes, we know we're in the ionic section. Then you have to ask yourself, is there a polyatomic ion? The way you can figure out if you have a polyatomic ion is that there will be 3 elements, 3 capital letters in the name. There'll be 3 capital letters in the formula. For the name, there is a table that lists all the polyatomic ions, and if any of the names match a polyatomic ion in the table, then the answer is yes. Okay, if the answer is no, then you ask yourself, is there a transition metal in the compound? If the answer is yes, we learned the rules for transition metals the other day. The Roman numerals are used to show the oxidation numbers, and if the answer is no, then you are at the simple rules of just writing the normal oxidation numbers and then dropping and swapping. Okay, so today we're going to take a look at what happens if you have a polyatomic. This is an extensive list of all the polyatomic ions there are. There will be a periodic table that was given, or there was a periodic table that was given to you that has a shorter list. You will be able to use this on any test or quiz. You don't have to memorize it, but you do have to know how to use it. So this is, like I said, sort of a extensive list. You have a shorter list that has the most common polyatomics. But notice a couple of things about this list. First off, every single polyatomic has at least 2 elements. Every single polyatomic has a charge to it, -1, -1, -2, -2, so on and so forth. The names on the polyatomic list, notice that their suffixes either end in ATE or they end in ITE. So that's very common for polyatomics, is that their endings, their suffixes are going to be ATE or ITE. Of course, I say that and then there's like an exception. but for the most part, you will notice that it is a polyatomic name and not a normal name because of the suffix ate, ite, or something entirely different. Like, for example, ammonium doesn't have any like suffix that you're used to seeing. So it'll be sort of off, and if you think the name is sort of off, it means that it's probably a polyatomic from this polyatomic list. So for writing the ionic formulas for polyatomic ions, if your ionic compound contains a polyatomic, you write the symbol of your metal and your nonmetal, you write the oxidation number of each ion, you drop and swap, and if you have a oxidation number other than 1, you have to put it on the outside of the parentheses of the polyatomic. Okay, so I guess an added step would be you have to make sure you have a polyatomic in the name, and that will go through with the next couple of examples. You'll be able to tell you have a polyatomic because it has like a weird suffix that will throw you off. So for example, you have ammonium chloride. So you get ammonium chloride, you try to search for the element ammonium on the periodic table, you can't find it anywhere, and that is because ammonium is a polyatomic. So ammonium is NH4 plus 1. This N and these 4 H's stay together. You cannot reduce, you cannot simplify, you cannot manipulate anything about the letters N, H, or 4. Okay? Chloride, we are familiar with that. That is chlorine from the periodic table. So it's going to take on a -1 oxidation number. Now, you are going to drop and swap, but when you drop and swap, the 1 from the chlorine has to go on the outside of NH4, and the chlorine will get the 1 from the NH4. Okay? Now, because it's sort of understood that there's one NH4 for every 1 chlorine if it's a 1-to-1 ratio, you actually don't need the parentheses if that subscript on the outside happens to be the number 1. If it was the number 2 or greater, then you would have to keep that parentheses there. Otherwise, you can just write NH4. So the 1 and the 1 tells you there is a 1-to-1 ratio between NH4 and Cl. Between NH4 and Cl. All right, magnesium hydroxide. Magnesium, that doesn't look weird, so that's just Mg from the periodic table. Hydroxide, though, biggest mistake is that hydroxide looks like it could be a normal nonmetal because it's the only one on the most common polyatomic list that does have a suffix of IDE. So it sort of looks like oxide, it sort of looks like hydride. So a lot of times people think it's oxygen or hydrogen, but it is special. It is hydroxide, which means that it is a polyatomic with the formula OH minus 1. Be very, very careful with hydroxide because, again, people often mistake it as a normal nonmetal and not as a polyatomic. All right, so when we drop and swap, so here, this 2 is going to go on the outside of the OH. So we're going to go OH2. The 1 from the hydroxide would go to the bottom of magnesium, but you don't have to write that 1. So what this tells you is in this formula, there is a 1 magnesium for 2 hydroxide ratio. Okay, again, it's very, very important that you put that parentheses. If you don't put that parentheses, you will get the problem wrong. Aluminum sulfate. So we have aluminum, that's not odd. Sulfate, though, sulfate has this weird suffix ATE. So that tells me I got to go look at my polyatomic list and I have to find sulfate, which is SO4 2-. So when I drop and swap, it's going to be Al2 parentheses SO4, and this 3 is going to come on the outside of the SO4. Sodium nitrate. Sodium, that's not weird, it's Na plus 1. Nitrate, again, the AT throws me off. So I'm coming over to the polyatomic list. I see that it's NO3 minus 1. So these two basically tell me that there is a 1-to-1 ratio between the Na and the NO3, and so I can write it like that. Okay, notice that I don't simplify the 3 from the oxygen. That is non-negotiable. What is simplifying is the one from the Na and the one from the NO3. Barium carbonate, barium is +2. Carbonate is weird, you got that AT ending, so you come over here, you see that it's CO3 2-. So here, let me write it all out, you would have Ba2 parentheses CO3 2. You can't simplify the 3 and the 2, that's non-negotiable, but you can simplify the 2 and the 2 to 1 and 1, and so it just becomes Ba1 CO3 1, and you can drop that parentheses because that subscript becomes a 1 now. Boron acetate. Boron is +3. Acetate is weird, so you come over here, see it on the polyatomic list. It is C2H3O2-1. So then this becomes BC2H3O2, 3 on the bottom. Let's do a couple of examples. Sodium nitrate, Na+1. Nitrate, it's not nitride. Nitride would just be N. A suffix of ATE tells me that I have to look at my polyatomic list, and I see that it's NO3. And if you notice, on this sheet, I have everything in parentheses, and then I have the oxidation numbers on the outside of the parentheses. The only reason I did it that way at the beginning was to show you that that oxidation number is for the entire ion, the entire like NH4, for example. But on the reference sheet that you get in class, you'll notice that the parentheses are not written. So just know that usually they're not written, but until you get used to the fact that that -1 for nitrate, for example, acts over the entire NO3, I have it written like that for the first day notes. So this one and this one are going to cancel, so you end up with NaNO3. This 3, again, it's there, but it does not simplify, or it does not have any bearing over the simplification between the oxidation numbers. Strontium phosphate, Sr+2. Phosphate, we come over here, we see that phosphate is PO4 3-. So here you'll see that I'm not going to write the parentheses around PO4. I'm just going to put the -3 up there, because by now, hopefully, you're sort of seeing that the oxidation number, what it does. So it'll be Sr3 parentheses PO4 and 2. The 4 and the 2 cannot simplify. Again, the 4 is entirely separate from anything else that we've been doing. You can only simplify if the subscripts from the drop and swap could simplify. Aluminum carbonate. So we have Al+3 carbonate, which is a polyatomic, is CO3 2-. This becomes Al2 parentheses CO3 3. And again, these 3's cannot simplify. Lead chlorate, Pb+4. Chlorate is over here, ClO3-1. This is Pb parentheses ClO3 4. Lithium chlorate, lithium is Li+1. Chlorate is ClO3-1. This becomes LiClO3 because those ones will simplify. Aluminum phosphate, Al+3. Phosphate is down here, PO4-3. This becomes Al3, PO4 3, and then these 3's can simplify to 1 and 1, so it becomes AlPO4. Calcium hydroxide, calcium is +2. Hydroxide, again, it looks like it should be a normal nonmetal because of the suffix IDE, but you have to just remind yourself that hydroxide is a polyatomic. So this becomes Ca parentheses OH2. Radium carbonate, Ra+2. Carbonate is CO3-2. You can simplify them up here in this step, so it's RaCO3. And that is where we will end.